So far we've got a table of values that we did in our first example. Like in this one, this -2 tells you that it opens down. And as soon as you find symmetry, you can find the rest of your graph. So we're going to look at one strategy to find symmetry, and this starts on page 253, and that's finding the x-intercepts. So if I can find the x-intercepts, maybe that helps me find my axis of symmetry and can help me find my vertex. So, how do you find x-intercepts? The x-intercepts on your graph are always where the y value is equal to 0. And they call these, as a result, they call them zeros. Sometimes they call them x-intercepts, sometimes they call them zeros. So if I plugged in 0 for y, well, I could divide everything by 2, then I could factor it, and it would solve that I have an x-intercept at -5, and I have an x-intercept at 2. I'm going to take out a dotted line here. There we go. Obviously, this is not in the right spot for my axis of symmetry. Right? I could take this dotted line. Doesn't look like it's in the middle yet. It's going to have to be halfway in between. So where would that be? Does that look like half? Is this half? Well, if you pick something, let's say I pick -1. It's wrong. But if you count, how far is -1 away from 2? 1, 2, 3 units. How far is -1 away from -5? 1, 2, 3, 4 units. Oh, shoot. So where should it be? And how can I find this? It's actually -1.5. How can I find that mathematically? If I know my two x-intercepts, I should always be able to find my axis of symmetry. So it has to be right in the middle. That is exactly, that connects to, remember doing midpoint in grade 10? Midpoint between two things, you could add them together and divide by 2. It's like finding an average. You had a test, first test you got 70, second test you got 80. Your average is 75. You could figure that out by saying 70 plus 80 is 150. Divide by 2, I get 75. Notice here, what do you get if you add -5 and 2 together? -3. -3 cut in half is -1.5. And so we know that our vertex is going to be somewhere, up here. Because I know it opens down. And I know that it's symmetrical, so it has to be on that line somewhere. I could plug in -1.5 in for x and actually solve to figure out where my vertex would be. So if we have our x-intercepts, we have symmetry already, we could find our axes of symmetry. And you want to highlight this. The x-intercepts are called the zeros of the function because they're where the y value is equal to 0. And then on page 254, I'm going to show you another thing that can help you with graphing. And they talk about it in your notes as the first differences. If we look at how things change, and I'm going to actually start at my vertex here. I go over 1, and this time I go up 1. So its first difference is 1. Then I go over 1 and up 3. Its difference is 3. Then over 1, up 5. Then over 1, up 7. If you're looking for a pattern, what do you think would be next? Over 1, up 9. So our differences go 1, 3, 5, 7, 9. I don't know if you noticed, but when I drew the first graphs at the very beginning of today, I was like putting dots quickly. I was doing that. I was going over 1, up 1, over 1, up 3. And this is always true if the number in front of your x squared is a 1. If it's a minus 1, you'll go over 1, down 1, over 1, down 3. If the number is something other than a 1, if it's a 2, watch what would happen if it was a 2. You'd go over 1, up 2, then over 1, up 6, then over 1, up 10, then over 1, up 14. If the leading coefficient is a 2, the 1, 3, 5, 7 pattern would double. If it's a 3, it would triple. So this 1, 3, 5, 7 pattern is really helpful for drawing something quickly. If you have your vertex, then you can quickly find other points, maybe even faster than a table of values. So when we get to example 2 here, we want to tell, based on the first differences, whether or not these are quadratic functions. Do they have that 1, 3, 5, 7 pattern or not? So I look. What's happening when I go from 2 to negative 1.5? I have gone down 3.5. If I do it again, negative 1.5, oh, I'm going down 3.5. I'm going down 3.5. Do you notice these are always going down 3.5? If that's always the same, that's a slope. That's a y equals mx plus b. This is a line. Right? And if every time I go over 1, I go down negative 3.5, can you see that makes a straight line? And it would have a slope of negative 3.5. So if your first differences are always the same, that would make a straight line. And unfortunately, table B, I think it does it again, right? Here we're going up 8.5, up 8.5 again. Yeah, it is up 8.5. This is another line. Up 8.5. Where the m value is 8.5. I guess in order to make sure these work, you should be aware that this has to stay the same. This is always going up 1. So let's just go back to one of the examples that they had, just so you can see one that is quadratic. Their table B, here it goes up 5. Oh, no, down 5, sorry. Down 5, down 7, down 9, down 11. Can you see the odd number pattern in that one? And an actual second way to tell something is a quadratic function, if you're looking at a table of values, is if you look at the second differences and they stay the same. When the second differences stay the same, that makes it quadratic. And he's looking at differences that way, that's kind of getting you already into calculus. What do you think would happen if the third differences were always the same? What kind of graph do you think that would make? An x cubed graph. So if the second differences are the same, it's an x squared graph. If your first differences are the same, it's a linear graph. So you can circle question number 6.